Now, this is a three-phase inverter. What you have, this is leg number 1, this is leg 2, this is leg 3. Now, in this leg, you have two switches, S1 and S4. In this, you have two switches, S3 and S6. Here, you have two switches, S5 and S2. Okay. The operation of S1 and S4 are complementary. S3 and S6 are complementary. S5 and S2 are complementary. What is the meaning? If S1 is on, S4 must be off. S4 must be off. This is called complementary operation. If S3 is on, S6 should be off. If S6 is on, S3 should be off. Always like this. So in the same leg, the two switches are never turned on simultaneously. Two switches of the same leg are never turned on simultaneously. Why? If you turn on this will be short circuiting the DC source. It will short circuit the DC source. Short circuit the DC source. So we avoid this. Okay. So if the two switches are on together, this is also called shoot through. This is called shoot through state. Now there is a special type of inverter that's called impedance source inverter, or quasi-impedance source inverter, where this is allowed, shoot through is allowed. Because what you do that, you connect some inductor and capacitors in the source side, so it will never be short circuiting the DC source. But when we shoot through this leg, it will cause the boosting of the voltage. The DC voltage is boosted. So here, like it is a kind of DC-DC boost converter. Is a kind of DC-DC boost converter. So you add a AC component in the source side. So in that case, you can shoot through the two states, and that will cause the boosting of the voltage. That happens in the case of impedance source inverter or quasi-impedance source inverter, because the source has impedance L and C network. Okay, but we are not going into that detail, but just you should have some background. So that's why I told you about this. Okay. So shoot through is not allowed in the normal voltage source inverter. It's never allowed in voltage source inverter, but it is allowed in impedance source inverter or quasi impedance source inverter. Okay. Now this voltage, the potential at this point, we call it leg voltage. This is called leg voltage or pole voltage. It's called leg voltage or pole voltage. Okay. And here, this is the point at which you connect the load. You connect the load. So this is star connected load. This is the neutral of the load. Okay. And this is the voltage, this AC voltage at the output. The AC voltage at the output. So this voltage which comes across the face of the load, that is called phase voltage. VAN is called the phase voltage across the load. Phase voltage across the load. This is called phase voltage across the load. And what is pole voltage? The pole voltage is the voltage at this point. Okay. So what will be the value of the, okay, one more voltage that I will tell you and then I will explain. This point we call the neutral of the source. Neutral of the source. Okay. Neutral of the source. Now, if you apply KVL, I can write like this. This voltage VAN Then in the loop, this is another voltage, VAN, small an. And then this voltage, VNN. So these are the three voltages. VAN, we call it pole voltage or leg voltage. VAN, small an, we call it phase voltage across the load. And VNN is called common mode voltage. Common mode voltage. Okay? Do you understand this point?
Yes.
Sir?
Now, you see, this common mode voltage is a culprit of destroying the bearing of the motor in a variable speed motor drive system. This VNN, that's the common mode voltage, this causes a common mode current that flows through the bearing and the shaft of the machine. And this will cause a frequent damage to the bearing of the motor. So that's why we have to reduce or eliminate common mode voltage. Now, this common mode voltage, we reduce or eliminate using certain PWM technique by modifying PWM technique, or we add common mode filter or common mode choke, at the output of the inverter in order to eliminate or reduce common mode voltage. Yes, Tamim.
Thank you, Doctor, but I think it's answered now.
Okay. Now, how we model this? Okay, now before going to modeling, let me tell you what will be the value of the pole voltage. What is the value of the pole voltage? How you write the value of the pole voltage? So let us see how we write the pole voltage. Do you understand all these pole voltage, phase voltage, and common mode voltage? Yes. This is not given in this way in the book. Okay, so you should pay attention here. Now let us see. Sometime the DC source is like this. You split the DC source in two parts, half VDC and half VDC. Okay, and you connect this point to this pole point. Okay, but okay, we will come to that later. Maybe for now you just look at the simple circuit. Now you see, you tell me what will be the pole voltage when this switch is on. Okay, also, why these diodes are there? Why these feedback diodes are there? Or anti-parallel diodes? Feedback, or we call it anti-parallel diodes. Tell me.
Because of RL load?
Yes, if there is RL load, we need to have the continuous path for the current, and when the switch is off, the current may go in the reverse direction through the anti-parallel diode. Okay, good. Now tell me, when the switch is on, what will be the pole voltage? What will be this voltage? Because you see, when this is on, this must be off, the lower must be off, because they are complementary in operation. So when the top switch is on, the bottom switch will be off. So what will be the pole voltage at this point?
VDC?
Yes, it is plus VDC. It is plus VDC. Okay. Now, what will happen when your lower switch is on? What will be the voltage here? 0 volt, because it is connected to the neutral point, 0. So the pole voltage will have plus VDC and 0, these two levels. Okay, two level. Now, if suppose your DC link is splitted in two parts, it is splitted in two parts, plus half VDC and negative half VDC. In that case, it will acquire two values. When upper switch is on, it will have plus 0.5 VDC. When the lower switch is on, it will have minus 0.5 VDC. These two will be the voltage level that you will see at the pole voltage. So either VDC and 0, depending upon the DC source type. If it is a splitted DC source, you will have half VDC minus half VDC. Overall is VDC, because you see total voltage will be VDC. Now, due to this pole voltage having only two levels, this type of inverter is called two-level inverter. This is called two-level inverter. Understand? This is called two-level inverter. Because the pole voltage will acquire two values, either plus VDC or 0. Two values, two levels. So it will be 0 VDC, 0 VDC, like this. So that's why it is called two-level inverter. We will come to multi-level inverter later, when we will have more levels. Okay. Now, I will write the modeling equation here that you can use to model inverter in the Simulink. You see, I write the KVL in this loop. So what equation I can write? I can write VAN should be equal to VAN plus VNN. Okay, I write like this. This is for phase A. For phase B, VBN plus VNN. Phase C, VCN, VNN. Do you agree with this?
Yes.
Yes.
I write this capital because this is DC. Okay. And I write this phase voltage as small because this is AC. This is AC. Okay. This is AC. We can write this also as small. Now, these are the three equations. You add them. What you will get? When you will add, what you will get? VAN plus VBN plus VCN should be equal to VAN plus VBN. This is DC. VCN plus 3 times VNN. This is what I will get. Do you agree?
Yes.
Now tell me, what is the sum of VAN, VBN and VCN? This is three-phase sine wave. So at any instant of time, if you add three-phase sine wave, what is the value that you get? Electrical engineers, tell me. At any instant of time, if you add three-phase sine wave, what is the value that you get?
0.
Exactly. So this is 0. But this is in a balanced system. If it is unbalanced, then it will not be 0. So I assume balanced system. So this is equal to 0. So from here, we can find out VNN. We can find VNN. VNN will be equal to negative of VAN plus VBN plus VCN. Let me see if I have given this or not. I have not given this model. Okay. Okay. This is what I will get as the common mode voltage. This is the expression for the common mode voltage. Now, I put this common mode voltage in each of these equations, and I will find out the relationship between the phase voltage and the pole voltage. Okay. So let me put this back into the first equation. So VAN should be equal to capital VAN minus 1/3 of VAN minus 1/3 of VBN minus 1/3 of VCN. So this will give me 2/3 of VAN minus 1/3 of VBN minus 1/3 of VCN, or I take 1/3 common, it will be 2 VAN minus VBN minus VCN. This is VAN. This is VAN. So the inverter is modeled in Simulink using this equation for VAN. Similarly, you can find VBN, you can find VCN. You put the same in here, you put the same in here. So what you will get? You will get the equation for the phase voltage and the leg voltage like this. The relationship between phase voltage and leg voltage. VBN will be equal to 1/3 of 2 VBN minus VAN minus VCN. And VCN will be equal to 1/3 of 2 VCN minus VAN minus VCN. This is what you will get. This is what you will get. So this is called model of a three-phase inverter, model of three-phase VSI, voltage source inverter. Do you get my point?
Yes. Doctor, why the neutral is different? Can't you connect the same to have them the same neutral, like same ground?
No, because this is the neutral of the source, and here you have the load, the motor, it has different ground. Okay. Even if you have the same ground, you will see some voltage across this. I'm not sure about the grounding. I have to check. But there is a voltage between the two neutrals. There is a voltage between the two neutrals. Okay. Because you have to see the KVL equation, you have to satisfy, and this gives you a neutral voltage, and you will see in the waveform also how it looks like. VNN, we have not drawn VNN. Okay, they have not drawn VNN, but you can draw it. You can draw it. You see how we can draw VNN. This is the same as your leg voltage. This will be the same as your leg voltage, VAN. I call it VAN, I call it VBN, and I will call it VCN. Okay. And why it is VAN, I will come back. When I will come back to this, when I'll come to this waveform, I will tell you how to draw VNN like this. VNN will be something like this. I will come back to this. Okay. So for now, you just see what is the equation for VNN. Equation for VNN is minus 1/3 of VAN plus VBN plus VCN. This is the VNN. Okay, and these are the phase voltage and line voltage. Phase voltage. Okay, line voltage is different. Now line voltage will be what? Capital VAB is your line voltage. So this is VAN minus VBN. VAN minus VBN is your line voltage. Okay. Now, operation mode of three-phase inverter. There are two operation mode. One is called step mode of operation or square wave operation. Step mode or square wave. In this it can be 180-degree conduction mode or it can be 120-degree conduction mode. These two conduction modes. What is the meaning of 180-degree conduction? Means each switch, this is your S1, this is your S4. So S1 will be on for 180-degree. We call it 180-degree conduction mode. And when S1 is on for 120-degree, we call it 120-degree conduction mode. Okay. That means, you see, in a cycle, you have 360-degree. In a cycle, you have 360-degree. So 180-degree, S1 is on, and next 180-degree, S4 is on. Okay. And in 120-degree conduction mode, for 120-degree, S1 is on, and next 120-degree, S4 is on. And the intermediate, there is none of them is operating. Okay. So this is not very attractive because it is not like, full utilization of the switch. So 120-degree conduction mode also is possible, but it's not practiced. Okay.
Would the 120-degree conduction mode produce 3-level?
No, it will have the same 2-level. You see why I called it 2-level? I called it 2-level because of this voltage. The pole voltage. The pole voltage will be only 2. When the upper switch is on, it is VDC. When lower switch is on, it is 0. So that's why it is called 2-level operation or 2-level inverter. Okay. Other is pulse width modulation, PWM of 3-phase inverter. So PWM operation, there are 2 types. One is called carrier based scheme, same as your single phase, but here there is no bipolar and unipolar. There is only one type, that is called carrier based sinusoidal PWM. What we do here, we have a triangular carrier wave and we compare with 3-phase sine wave. 3-phase sine wave. Okay. That's the PWM. There is another PWM called space vector PWM, where the reference voltage is considered as a space vector. So we'll come back to that. So now let us see the 6-step operation. 6-step operation or the step mode of operation. The step mode of operation, what we assume that my switch S1 is on for 180-degree and next 180-degree S4 is on. So I show here the switching signal. This is the switching signal. That means this is the signal that is given to the switch S1. So when I give this signal to S1, it will remain on from 0 to 180-degree. 0 to 180-degree. S1 is on. And from 180-degree to next 180-degree, from 180-degree to 360-degree, S4 is on. Do you understand this?
Yes.
Okay. So what will happen to S2? Sorry, S3. We'll start from S3 because this is upper leg. Okay. So upper switch. So S1 is operating from 0. It starts from 0. It goes up to 180-degree. Then S3. Okay. And S4 starts from 180-degree, goes up to 360-degree. Now what will happen to S3? Tell me from where it should be on. What is the phase difference between these two? What is the phase difference between these two?
120.
120-degree. That means after 120-degree of S1, S3 should be on. So you see, it starts after 120-degree, 2 pi by 3, 120-degree. And then for how long it will remain on? It will remain on for 180-degree. Because each of them has to remain on for 180-degree. So it will remain on for 180-degree. That means it will stop here. So when it is stopped here, what will happen? This switch should be on. That means S6. So S6 will be on here, and in this remaining period here, S6 is on. So S6 is on from here to here. Do you understand this?
Yes.
What about S5? S5 will be after 240 degree of S1. So it will start from 240 degree. So 240 degree is where? If this is 240 degree. So this will remain on for 180 degree. That means these two and then one more here. So this is 180 degree. And where the bottom switch will be on? S2, where the S5 is not operating. You see, in this gap. In this gap, S2 will be on. So it is drawn here, S2. This is drawn here, S2. Do you understand this point? How the switching signal is plotted? So this is called the switching signal or the gate driver signal that you give to switch S1. This is to S2, this is to S3, this is to S4, this is S5, S6, S5, S6. So I will fire or trigger S1 here. I will trigger S1 here. S1 will be triggered here. And it will be off at this point. This is on point, this is off point. So gate signal will be withdrawn or the base signal will be withdrawn at this point. So S1 will be off. And as soon at the same moment, I give the triggering signal to S4. But you see, I told you one thing, practically, they are not at the same instant. We give some gap for the starting of S4. So turning off, because you see, turning off will not be immediate. It will be like this. So once we make sure that it is completely turned off, then only we start S4. This gap, we call it delay time or dead time. This is practically. But ideally, at this point, S1 will be on. At this point, S1 will be off. At the same point, S4 will be on. And at this point, S4 will be off. So we will draw the signal. Okay. Then what will happen? You see, we trigger S3 at this point. And we turn it off at this point. Then after 120 degree further, we on it here and we off it here. Okay. Now, if you look at this sequence, at what sequence these switching signals are given, you see, S1 is on here, S2 is on here, S3 is on here, S4 is on here, S5 is on here. And that is why we gave this numbering 1, 2, 3, 4, 5. And what are the off period? Here, this is off, 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 off. So, do you understand this point or not?
Yes.
And you see, this is why we give the numbering like this, because the switching is happening like this. After S1, 60 degree, after that is S2, 60 degree, after that we fire S3, after 60 degree we fire S4, after 60 degree we fire S5, and after 60 degree we fire S6. Okay? And we withdraw the signal in the same sequence like this. Total period of 360 degree, you can divide them in 6 modes or 6 intervals, six sub-intervals. This is sub-interval 1, this is interval 2, or interval 3, interval 4, interval 5, interval 6. Or we call it mode 1, mode 2, mode 3, mode 4, mode 5, mode 6. Now, you see here, from 0 degree to 60 degree, this S1 is on, S5 is on, S6 is on. So I write here what are the switches that are on in this subinterval S1, S5, S6. Similarly, in this interval S1, S2, S6, S1, S2, S6 is on. So each subinterval you see that 3 switches on. So each interval you see that 3 switches on simultaneously. Then here S1, S2, S3. Then here S2, S3, S4. Then here S3, S4, S5. Here S4, S5, S6. Now, any question up to this point? You see, when the switch 1 is on, what is the pole voltage? Is V plus VDC? Yes. So this also, this will be your, if this is your VAN also. VAN will be the same. It has the value plus VDC. When switch is on, VAN is, or pole voltage is VDC. And from here to here, the pole voltage will be how much? Tell me, what is the pole voltage VAB? VAN will be equal to how much? When S4 is on, what is VAN? Are you with me?
Doctor?
Yes. What is the value of VAN? VAN, the pole voltage, when this switch is on?
Should it be 0?
0. So it is 0. From here to here, it is 0. And from here to here, it is plus VDC. Now, you see, this is for S2. This is S2. S2 is where? S2 is here. Yes? S2 is here. So, in this period, your VC is, from here to here, your VCN is 0. Yes? And in this period, your VBN is plus VDC. When this is on, VBN is plus VDC. And here, your VCN is plus VDC. Here, your VCN is plus VDC. So you can consider this as VDC, VAN. This is for VAN is equal to VDC. This is for VBN is equal to VDC in this period from here to here. And for S5, this is VCN is equal to plus VDC. Okay. Now I will find out what is the line voltage VAB. What is line voltage VAB? So VAB is VAN minus VBN. Okay. So how we get this waveform? How we get this VAN? This is VAN, this is VBN, this is VCN. So there is a calculation for this. We can do it in two different ways. One is from the circuit operation. One is from the circuit operation. The other is from the modeling that I gave you the expression for. So let us see first how we get it from the circuit, and then I will explain you how we can get it from the equations that I explained you, and which is not given in the book. Yes.
Doctor, you said that this is VAN, VBN, but the graph says it's the line voltage.
Yeah. This is phase voltage. This is not the leg voltage. This is the phase voltage. Okay. These
I
are
mean
the
on the
leg
graph.
voltage. This is the leg voltage. I consider this as a leg voltage.
Yeah, but down like
Sorry.
below
This is
the
not
graph.
VA.
Yeah.
Sorry. This is sorry. I'm sorry. Yes, thank you. This should be not be VAB. This is like VAB. This is sorry. Yeah, this is VAB. This is VBC and this is VCA. These are the line voltage. I have to plot these line voltages. Okay, I have to plot these line voltages. Now, to plot the line voltages, I will use circuit approach, which is given in your book, or the modeling approach that I will explain you separately. So let us see how. So in this mode, first mode, the switches that are on are S1, S5 and S6. Okay, S1, S5 and S6. Now let us draw the switching diagram. So S1 is on. This is my phase A. S1 is on. And what else is on? S5 and S6. S5 and S6. So S3 is off, that means. This is S5. This is S1. Okay. And here this is S6. And this is your connection point. Here is your connection point. This is your A. This is B. This is C. This is N. Do you follow this switching diagram? Do you understand what I did?
Yes.
This is plus VDC. This is minus. Okay. This is now redrawn in this way. How? You see, the positive of the VDC is connected to S1 and S5. So I redraw it like this. Follow me. This is my VDC. The positive of VDC is connected to through S1 to A and through S5 to C. Yes.
Yes.
I assume resistive load. So it is connected to S1 and this is connected to C. So this is This is A, this is C, and this is the neutral point. This is my resistance. And the B is connected to the negative. You see, B is connected to the negative. This is B. Please tell me if you understood this or not.
Understood, doctor.
Now, this is R. This is R. And this is R. Now, what we will do is, we will find out what is VAN, the phase voltage. We will find out what is VBN, the phase voltage. We will find out what is VCN. And then we will find out VAB, VBC, and VCA. 6 things we will find out from this circuit. Okay. Now, you see, these two are in parallel. These two are in parallel. So I can redraw the circuit like this. The parallel combination of R and R will give you R by 2. Will give you R by 2. Will give you R by 2. This is point A, comma C. This is point N. Voltage across A, VAN and VCN will be same because they are in parallel. They will be same. Okay. And the current will flow in this direction. So it is plus, this is minus. And current is flowing in here in this direction. So this is plus and this is minus. That means voltage across B N is negative polarity, opposite polarity. It is opposite polarity. Now I have to find out what is this voltage, because you see now this is one source and it is supplying voltage to the two resistances. They are connected in series. So what is the voltage across AC? You can use voltage divider rule, or you can find out first current and then you find the voltage. Okay, let us apply the voltage divider. So what will be the voltage across this R by 2? That is AN is equal to VCN will be equal to R by 2 divided by R plus R by 2 multiplied by VDC, multiplied by VDC. This will be the voltage across AC or AN, AN and CN. Do you agree this? With the voltage divider rule?
Yes.
So what will be this value now? This will be equal to VDC by 3. Yes? 2 and 2 cancels out. R and R cancels out. So what you have is VDC by 3. Yes?
Yes.
Okay. Now, what is the voltage across BN? VBN? VBN. It will be negative voltage because it is opposite polarity. What is the voltage? What is the resistance? R divided by R plus R by 2 multiplied by VDC. So this will be equal to minus of 2 VDC by R, minus of 2 VDC by 3. Is it clear?
Yes.
In this interval, from 0 to pi by 3, the voltage across AN and CN is VDC by 3, while voltage across BN is minus 2 VDC by 3. I got this. In the same way, we will find out for all the other 5 modes. I'll find out for all the 5 modes. I'll do one more and then you have to do. Now, so first thing, let us see in this pi by 3 to 2 pi by 3, what are the different switches that are on? See, what are the different switches that are on? S1, S5 and S6. S1, S2 and S6. S1, S2, S6. So let us draw the switching wave diagram. So S1 is on, lower one is off. Then S2 is on and S6 is on. So that means this is on. This is on. So here you have resistance. Here you have resistance. Here you have resistance connected like this. Okay, this is plus VDC like this. Now I redraw it. So you see here, if you redraw, positive is connected to A, and negative is connected to the parallel combination of this is connected to B and C, and this is plus and this is minus. This is R, this is R, this is R. Then I will further make this change. Now you see, you can see that VBN will be equal to VCN because they are in parallel. Okay, and they will be negative because current is flowing in the opposite direction in this. Both VB and VC will be negative. VA will be positive because current is flowing in this direction. So now I will redraw this. This is A, this is B, comma C. This is N. This is R, this is R by 2. So now I will use again the voltage divider rule. So with voltage divider rule, VAN will be equal to R upon R plus R by 2 times VDC. This gives you 2 VDC by 3 as your answer. And what is the voltage here? You see, this is plus, this is minus, opposite to VAN. Here it was plus here and minus here. So VBN is equal to VCN is equal to minus of R by 2 upon R plus R by 2 into VDC, and this gives you minus VDC by 3. Do you get my point?
Yes.
Yes, doctor.
Okay. So I will stop here now and we'll continue from this. But what I want from you now, you please solve for mode 3, mode 4, mode 5, mode 6. Okay? Because here only mode 2, mode 3 is given. So you mode 3, 4, 5 and 6. Please complete this. Once you know all this, then we will straight away we will plot the phase voltages. So you see here, the VA and VB both will be VDC by 3. So VAN is VDC by 3. This is VDC by 3. This is minus 2 VDC by 3. Next interval, it is plus 2 VDC by 3. This is minus 2 pi by 3. This is minus pi by 3. Minus 1/3 of VDC. So this is 6-step waveform. How? 1, 2, 3, 4, 5, 6. 6-step waveform. This is phase voltage. Phase voltage across the load. So this is also called 6-step operation of inverter. Now tell me, what is the switching frequency of the device? What is the switching frequency of the device? At what frequency it will switch? I explained you this switching diagram. So in half cycle, it will remain on, half cycle it will remain off. So it will switch only once in 50, suppose you have 50 hertz cycle. So if suppose I am getting 50 hertz output, so for 50 hertz output, it will switch on only once and then switch off, one on and off. So the switching frequency will be only 50 hertz. So switching frequency is fundamental, is equal to the fundamental frequency. It will only switch on once in all 50 hertz. I mean. So it will on and then it will off. So one on, one off in 360 degree. So if it is 50 hertz output, what will be the time from here to here? For 50 hertz output, what is the time? 0.02 second or 20 millisecond? So 20 millisecond will be the total period. In the 20 millisecond, 10 millisecond it will be on and 10 millisecond it will be off. So it is switching only at 50 hertz frequency. So that's why the switching losses are very less in this case. But the voltage, line voltage, we will see that it will be like this. I will come back to the line voltage again. Line voltage is like this, and the phase voltage is 6 step. And when we do the Fourier analysis of this, we will see that it has strong harmonic components. So then we go for PWM. We go for PWM. That means here we have many pulses. We have many pulses. We have many pulses like this. That will be PWM. Okay, so we'll come back to this again and